Osmotic pressure and colloids. So this is another colligative property of solutions. Osmosis is the selective passage of solvent molecules through a semi-permeable membrane from a dilute solution to a more concentrated solution. So what's happening is the solute molecules or atoms aren't moving, but the solvent is. So in this case, it's higher concentration on this side than this side, so the solvent wants to go this direction to make the concentrations equal. Nature doesn't like it when concentrations are not the same. And so this pressure is osmotic pressure. So they use pi as the symbol for that. So pi equals I mert, where I is the Van 't Hoff constant, right? 1 for molecules. We'll talk more about it later. M is molarity. R is the universal gas constant with pressure, liters, atmospheres over moles, Kelvin, and T is temperature in Kelvin. So you could calculate the pressure based on the concentration of the solutions and the temperature. Semi-permeable membranes allow the passage of solvent molecules, as we said here, right? But solute molecules don't move across. And the pressure required to stop it. So if you pushed back on it and measured that pressure, that would be the osmotic pressure. And we see this in biology a lot. So if we have a cell, right, an isotonic solution, and you should know these terms, means that the concentration outside is the same as inside. So I'm going to put 5 on the outside and 5 on the inside. So the solvent, right, is happy with that. The concentrations are equal on both sides of the cell. So nothing happens. Hypotonic solution, what that means is the concentration outside, I'm going to put my 5 out here, is lower than the inside. So hypo means less, so there's less solute molecules in the solution, there's more in the cell. Water now wants to equalize the concentration, so there's a gradient where water now wants to come across and dilute the higher concentration inside the cell, and the cell doesn't like that and it explodes, all right, puffs up and then blows up. Hypertonic means there's more solvent or solute molecules on the outside than the inside. The water now wants to move out, right, to dilute the outside, and so that's why the cell looks shriveled. It loses its water. We've been talking about this Van 't Hoff constant, I. And remember, colligative properties are properties that depend only on the number of solute particles, right? Not on the nature of those particles. And so if you looked at a 1 molar or 0.1 molar sodium chloride solution, what we know is that it'll be 0.1 molar in sodium ions, right? And 0.1 molar in chloride ions, right? So what that means is the 0.1 molar solution of sodium chloride is really 0.2 molar, right? 0.1 plus 0.1 molar in ions. And because colligative properties don't care on what those natures are, what the nature of those solute particles are, only on the number, because this ionic compound brought 2 ions with it, right, 1 sodium and 1 chloride, the effect, right, the colligative property effect will be twice as high. And so that's why we include I to correct for that. If you had a molecular solution, you'd have some effect, right? If you put sodium chloride in there, you'd actually have double the concentration of particles as you'd expect, so you have to use an I equals 2. Right? So the 0.1 molar solution acts as 0.2 molar ions in solution. The actual number of particles in solution after dissociation divided by the number of formula units is a way you could calculate it. But basically, you just need to look at it. So sodium chloride, you can see there's 1 sodium ion and 1 chloride ion. That's 2 ions, so I equals 2. Calcium chloride, we see there's 1 calcium plus 2 and 2 chloride ions, right? So 1, 2, 3 ions, I equals 3. So this is how you can, basically you just look at this qualitatively and decide. So, and this is only true for ionic compounds, right? Molecular compounds, because they don't dissociate into more particles, right? I equals 1 for those guys. So here, potassium iodide, what is the Van 't Hoff factor? It's an ionic compound, 2 ions, a K plus and an I minus, so I equals 2. Here, calcium nitrate, right? This dissociates into 3 particles, right? There are 3 ions, calcium ions and 2 nitrates, so I equals 3. Urea, all nonmetals, right? This is a molecular compound, so I equals 1. And then finally, sodium phosphate gives me 3 sodium ions, right, and 1 phosphate ion. So I would be 4 for this guy. So we can include that in our calculations now. If you do a boiling point elevation or a freezing point depression or vapor pressure lowering problem with an ionic compound, you have to consider I, the number of ions that are formed in solution. I. All right, colloids are kind of related to solutions, but a little bit different. So a colloid is dispersion of particles of one substance throughout a dispersing medium of another substance. That sounds a lot like a solution, doesn't it? If you have your solute dissolved, we got to go to red pen on this one. Oh, we'll try green. If you have your solute dissolved in the solution, right? If it's completely dissolved, it's a solution. Colloids, the particles are generally larger than in solutions, and the suspension is not as homogeneous. So you can kind of think of these guys as being bigger, and they're not quite solubilized like they would be in a true solution. You look at a true solution and you can see it all looks the same, right? You can't see the little green particles. When you look at a solid colloid, sometimes you can see. And the so-called Tyndall effect is if you shine a light through it, if you can see the beam, that indicates it's a colloid. When I shine the light through the solution, you can't see the path of that beam. And what's going on here, right, is that the light is reflecting off of these particles. And so we're actually seeing reflections of the light, and so we can see the beam. So dust in the forest, this is another example of a colloid. Words that go with these things are sols. If you have a solid dispersed in a liquid, so jellies are an example of that. Emulsions are examples of colloids, so a liquid-liquid emulsion like mayonnaise, milk, these are examples of emulsions. Foams are gases dispersed through liquids like whipped cream, classic. You can have a solid sol, where a sol is dispersed in a solid instead of a liquid. Glass, I guess, alloys, these aren't super fun. Solid emulsion, so you can have a liquid in a solid like butter or cheese. Solid foams, right, so meringue. The foams you use to insulate your house, those would be solid foams. Aerosols, this is when you disperse solids through gases or liquids in gases. So smoke, dust in the air, bacteria in the air. These are examples of solid aerosols. Liquid aerosols would be things like fogs and mists and sprays. So you should recognize then what an emulsion is and what an aerosol is and what a foam is. You don't need to know these specifically, but just have an idea. Colloids in general can be described as either hydrophilic, right? Hydro meaning water, philic means loving, so they love the water, or they can be hydrophobic, where they fear the water. Generally, water-loving or hydrophilic colloids are more stable. The hydrophobic ones, they're not quite as stable, and they can crash out, where you get your solute precipitates out eventually. So not quite as stable as many hydrophilic ones. All right, last thing to think about here is detergents and how they work. And so what we have these are detergent molecules, the simplest form, right? What you have is this is a carboxylate, the charged form of a carboxylic acid. What we have is a long non-polar tail, right? This is non-polar, so primarily London dispersion forces, right? At the end, you've got this charged, right, resonance stabilized charged head. And so this is the polar end, and this is the non-polar end. And so what happens is when you put them in water, the non-polar parts want to interact with themselves, right? Like dissolves like, they're happier. The polar parts want to interact with each other. This is how you get cell membranes, right? You get this guy. But what's going to happen with dirt is, if it's non-polar dirt, the non-polar parts of the detergent interact with it until it's completely surrounded. Now the non-polar dirt or grease is happy because it's interacting with non-polar tails. It's in a non-polar environment. And the polar heads are interacting with polar water, so they're also happy, right? And so what we've made is something called a micelle, right? And now this guy can float away and go down the drain, right? So now my fabric is nice and clean. And you can see there's different examples, but we recognize that you have polar heads, and these are all C's and H's, right? These are non-polar regions. So you can have you'll have polar regions and non-polar regions. So a big, long, non-polar chain and a charged polar head. Here's another example. Triton X100 is this guy. He's got a non-polar head and this slightly polar tail. He's actually a big polymer here. So this is how detergents work. And basically it all boils back down to like dissolves like, doesn't it? All right, that's it. Stop.